Welcome you all to the UNU-INWEH public event, the Science Talk. For those of you joining us for the first time, we are glad you can make it today. Thank you very much. I am your host, Professor Grace Oluwasonya. Before presenting a distinguished speaker or speakers as it stands out today, please note that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions that you may have. Please type your questions or comments in the Q&A chat box, and we will pick them up from there. Thank you. The topic of today's talk is water as a working fluid for a sustainable future. Contribution from chemical engineering. In fact, I'm so excited. So let's talk. Our presenter for today is none other than Professor Irina Smirnova. I hope I got the pronunciation right. Professor Irina is a full-blown professor and the head of the Institute of Thermal Separation Processes and vice president of research at the UNU Hub, Hamburg University of Technology in Germany. Our research interest is in aerogels, high-pressure technology, biorefinery, separation technologies for life science and molecular thermodynamics methods. Among others, she is a member of ProcessNet Working Party, Thermodynamics, Adsorption and Thermal Separation, the chair of the ProcessNet Working Party on High Pressure Technology, and the vice chair of the International Association on Advances on Supercritical Fluids and chair of the International Conference on Aerogels. Professor Irina is well published with at least 237 papers, 47 of which are in high index journals, 7 patent applications, and at least 1 book chapter. I am excited to introduce Professor Irina Smirnova. Please join me in welcoming Professor Irina and, of course, one of our doctoral students, Razan Altarabeen, for today's presentation. I hope I did not massacre the pronunciations. So the floor is yours. Take it on.
Thank you very much, Grace, for this fantastic introduction. So we are you're very grateful for that, and we are very grateful for the possibility to have this talk now. And this is very exciting that through this UN University Hub, we are now connecting to you and connecting to the whole world. So that's absolutely great opportunity for us. So I know that your lecture series is more about water, also from the global, from the big point of view. But today we would like, Razan and myself would like to have a little bit different view on this topic from the point of view of the chemical engineering. And so maybe that will be a little bit different talk for many of you, but we did our best to make it understandable, and we do hope that you will be excited about the participation and contribution of chemical engineering to the topic water and of use of water as a kind of working fluid. So why water actually? We see as chemical engineers that water is a very peculiar liquid in many, many different respects and many perspectives. First of all, for sure, this is a life matrix, but from our point of view, this is the only substance that exists on the Earth in all 3 aggregate states. It can be liquid, it can be gas, it can be solid, it can be ice. So no other fluid exists on the Earth in all these conditions at the same time. We have plenty of water. It covers 71% of Earth's surface, but nevertheless, our use of water is still maybe has some potential. So this is what we want to show with this talk. But besides being so abundant, besides being a most well-known liquid to the humankind, we are still on the way to understand how to work with water, how to use water for our research, for industrial needs, and for our industrial society. So the most important point here today is to see that water behaves very differently in comparison to all other fluids. And this is what we want to show, and this is something what is well known. If you remember the Industrial Revolution of the 19th century, we all know that it was driven by water as a working fluid. What does it mean? When you look at this and this train, for sure you all, that doesn't matter from which country you come, you know this situation, this big vapor coming out. This is water which was used for the engines, which was used for energy production. And from this perspective, we have this term working fluid. So what does the working fluid do? What does the water do from the point of view of engineering? It has a transfer function. It transfers force, motion, or mechanical energy in different apparatus. And what I have here is a little sketch. We have a turbine which produce energy because we use the energy of water being heated, being brought on the different pressure level, and having an ability to convert the internal energy which it has as water as a different temperature and pressure states to the mechanical energy. We can let the turbine work, we can let it mechanically act. And that is why we say water is a working fluid, letting us a possibility to convert heat into work. And this is one of the most important laws of the thermodynamic, how we can convert heat and work into each other. But what we have asked ourselves, not in the years of Industrial Revolution, but in the year 2024, what we are now at our university is, when the water was used in the macroscopic scale in that time as a working fluid, can we maybe today make still use of water as a working fluid, but at the micro scale? Can we look how water behaves in the devices which are not in the cubic meter scale, but which are in nanometer scale? So we have maybe 10 orders of magnitude, which is in between this engine and our target materials now. So what is our target is we want to have materials having nanopores inside them, so porous solids, which include fluids, and we want to use water on this scale again as a working fluid in analogy to the former time, to the engine solutions and different devices. And this thought was included in our initiative Blue Materials, materials combined with water, that is why blue. And maybe some of you who have some imagination of Hamburg can realize on this picture some very important symbols of Hamburg. This is our Elbphilharmonie, our very famous musical hall. We have here the TV tower, and we have our Elbe River. So we have plenty of water in our city, and we would like to use this water in this nanoscopic scale in this initiative. And I would like to show you just some little examples out of what we are doing here in this initiative. We would like to combine structured materials, nanoporous materials, with water, and we would like to show how water can bring new functionalities in these materials. So if we, for instance, look at this picture, which shows us mechanical actions being inspired by nature, what we see here that also the plants can make use of water for the mechanical action. So you see this here, two states of this part of the plant. When we have sunny weather, it's open, and we have a rainy weather and a lot of humidity, it closes. So the presence of water in this biological system leads to the mechanical action. And this is what we want to mimic. In our case, we want to have an actuation in the porous materials. It means when the water come in, they change their mechanical state, they change their volume, they change their shape, and in this way we can make an actuation which is reversible. Water lets these materials, for instance, swell and shrink in reversible way many times, and we don't need any mechanical devices. This is just water leaving for this actuation. Then we have an area of photonic materials. If you look at this little chameleon, all of you know that chameleon can change the colors. And this color changing is because of the different scattering on the skin of this chameleon. And what we are doing, we are in the teams of our university have found a possibility to use the porous matrix, which is in the wet state, has a different color as it has in the dry state, and then it can change the colors there and back again reversibly. Why do I speak about this reversibility so often? Because for us and the engineers, when we make the devices out of these materials, it's important that they have certain lifetime, and all this effect should be able to be repeated many thousands of times. That is why this reversibility. And there are a lot of more examples. One of them is, for instance, here in the type of the energy material, where we have the materials in the wet state being charged and being able to produce electricity, and in the dry state being non-charged, and then to be able to give this ability away. So this is something what we are looking for, and the principle of all this research is this water coming inside the pores of materials and interacting with them. So having told this, I would like to show you the example which I was just describing with this chameleon with the color changes. We have here a modulated porosity. So we have the porous materials with the channel inside. It's based of silica, and in this based on silicon, and in this channel we have a certain scattering of light. When this channel are dry, then the scattering is in the direction that the material looks magenta. So this is what you see here in the downscale of the right side. But when water comes inside, although the water itself has no color, the scattering of the light changes because of presence of water, and these materials change this color to blue. And if I'm lucky and this video works, then oops, back. We try it again. I think I clicked to press logo. Yeah. Let's try again. It worked yesterday, so it should work today as well. Just a sec. Sorry, it should work actually. Okay, it doesn't work. Actually we wanted to we tried it yesterday, and it was working. So I just try one more again. So it was I wanted to show you in the real time how it works, but it doesn't let me. So no. So what you would see here, if this video would work, we would see that this is just a matter of seconds. When this dry matter is in contact with water, is infiltrated immediately, and after this infiltration, the material gets blue, but then the water is coming out, the water evaporates, and the materials get dry and goes immediately back in this state. So this is something what we can do, and you can imagine when you, for instance, drive a car and you are under the rain, your car now has a different color as before. It is now known by the interaction with the temperature, but it's not so known for the interaction with the water. So the water can introduce the color change, for instance, in this system. Another example about the energy. So what we can have here, there is, if you look at this small cycle, we have material having again the pores, and when the water comes into the pores, it interacts with the matrix, and then this capillary is filled with water, and then by the interaction we have the ion exchange here, so we have the charging of our surface, and since we have a charged surface and we have water inside, we can produce the electrical current for this out of this device. Then we have a drying cycle, the water evaporates, it discharges, and then it comes back into the level before, so into the situation before. Then we can wet it again, and we can go several times. And what you see here, and I hope this video will work, we have now our Philharmonie. It's the Elbphilharmonie in Hamburg, and I told you we have a lot of water. And now imagine we take these materials, and in the Elbe River we have the different tides. So we have the high water level and the low water level several times a week, obviously every day. And then you can imagine when this water goes up and we have introduced this material here on the basement, it gets wet, so we can charge our, let's say, phone here. And when the water goes down again, because the water level in the river goes down, that it gets dry, and then it comes back into the original state. So this is a possibility due to the natural presence and natural tides of the water to use, for instance, these parts of the building being decorated with these materials as electricity, as a power provider. So this is our dream, how we can use it. For sure, there is a way up to we are allowed to build it in the Elbe River, but this is what we dream about. Again, let's say the water has different properties, and these properties depend not only on the presence and absence of water, but the water itself changes the property depending on the temperature and pressure. And when we don't think about the natural situation, but we think about the chemical apparatus, we can change the temperature and we can change the pressure in the big variety of the range. And when we think about water as actually very polar compound, which is able to dissolve very, very polar substances, and now we look at this ability at different temperature and pressures, we will find out that this changes. It means that when we heat up the water up to, first of all, 100 degrees, 200 degrees, 300 degrees, and we keep the pressure high so that the water doesn't evaporate by still liquid, and we look at the property of this water, we will see that the dielectric constant, which is this graph, goes down. What does this mean? It means that the polarity of water changes, and now water is a different solvent as it used to be before. It means I can dissolve more unpolar substances in comparison to the situation, let's say, at the 25 degree. So how can we use this? When do we need to dissolve the unpolar substances? It's always a situation in the chemical engineering when we need to use organic solvents. Why do we use organic solvents? Why we need to dissolve something which is not soluble in water. By changing the temperature of water and changing its pressure, we start to be able to use water instead of organic solvents, because the dielectric constants allow us this. We can also look at very many different properties. When we look, for instance, at the density of water, we will also find out that the density goes down when the pressure, temperature goes down, but this is not unusual. It happens with almost all liquids, but also ionic, so-called ionic product of water has a very abrupt change here. It also goes down. It also tells us that the self-dissociation of water changes and it gets less polar. So for which process can we use this? We can use this for the process, for the sustainable processes which are used biomasses. And this is what I wanted to show you, and this is a courtesy of one of our colleagues. You see here downstairs a sample where you have a piece of wood. This white piece is a piece of wood. And when you contact the piece of wood with water, everybody of us knows nothing happens. The wood maybe gets wet, but that's it. But if we increase the temperature to 340 degrees C and increase the pressure to 100 bar to keep water liquid, and then we wait 1 minute, 2 minutes, 3 minutes, 4 minutes, and 5 minutes, we will find out that the wood dissolves completely. It means I can really dissolve wood in water, what was not possible before. So we have a modulating properties of this liquid, and it gets a very, very powerful solvent at these conditions. So speaking about water, how we can use it for the sustainable process. Now there is a big wish to use biomass for all different types of the production. And when we look at the biomass, for instance, the straw, we will find out that in the biomass we have three important parts. This is the cellulose, this is the lignin, and this is the hemicellulose. So these are three polymeric materials, natural polymeric materials, which makes the wood, which makes the biomass very, very strong when they come together. So this is like a concrete, which is quite strong, and it is very difficult to break these three parts apart. And that is the struggle, and this is a challenge of the so-called biorefineries, which try, instead of oil, to use the bio-based solutions, for instance, to use biomass and to break it, to fractionate it. We can use different organic solvents, but let us think, can we maybe use water? We have seen that the water can dissolve wood. Can it dissolve the other biomasses? Can we use it for straw? Can we use it for all different annual plants, which are very potential future feedstock for our production? And the answer is very positive. So we can use water as a solvent. This is a so-called outer hydrolysis process, which takes place when we combine high temperature liquid water with the biomass, and we start this dissolution process, which we have seen before in this little example. We could show in our work, and also the biorefineries based on different plants could show that by using water and increasing the temperature stepwise, we can stepwise dissolve the different fractions of the biomass. If we go back, we can first dissolve the hemicellulose by the moderate temperature, then we go for the cellulose at the higher temperature, and at the end we have high molecular weight lignin, which is left over and which we can use further, for instance, for the different processes. And this is something which we work in our institute. We want to make a full fractionation of the lignocellulosic biomass. We want to convert it in high value products, and we want to do it with the help of water, not to have organic solvent and not to have an ecological negative impact on this case. But there is a big way out of and along this development. We have done it in many, many projects. So we think about a sequence of the step. We have here a biomass, so these are the straw pellets, and then we have a different extraction steps. We first make extraction of oils and phytophenols and so on. This is the one step which we pre-treated. We make it with a supercritical carbon dioxide, which is also very abundant solvent. And then we contact this biomass now with water at low temperature. We can extract proteins, we can extract amino. We increase the temperature, we can extract the hemicellulose and some soluble lignin molecules. We increase the temperature further, and now we can extract all the cellulose, and then we have a lignin as a leftover. If we increase the temperature even further, we can liquefy everything, and then we really literally converted the solid biomass into the liquid without any residue. And this is the power of water at different temperatures and pressures. This is what happens. This is a little picture from our institute. We have here a demonstration scale biorefinery at the 40-liter plant. What you see here on the right-hand side are our equipment in which we can connect the biomass with water, where we can make this dissolution process. And I have brought you the internals of this apparatus, how it looks like inside. Look, this is our biomass which we fill in, and now we start to contact is with water. The water comes from down to the top, and this is 1 minute, 3 minutes, 7 minutes, and 20 minutes. And what you see here, that the water comes into the biomass swells, and you see how it raises inside the equipment. It takes the whole space of the equipment, at the same time the dissolution process start to take place, and we dissolve slowly, fraction by fraction, this biomass, and take it out fraction by fraction from our equipment, like they do it in the refinery with the crude oil. Exactly the same principle, but not with water. And what I told you in the beginning is we can dissolve the solids, we can dissolve the hemicellulose, we can dissolve the cellulose, and now the lignin is left over. And on this spot, I overgive to Razan, to my PhD student, who is making something very valuable out of this lignin, and she will show you how she can use this lignin after it has been extracted with this hot water. So please, Razan.
Thank you, Professor. And as Professor Smirnova mentioned, one of the most important fractions we get after using the water to fractionate the biomass is lignin. Lignin, in terms of abundance, it comes second after cellulose, which means it's available in huge amount in the nature. And it's also produced as byproduct by the paper and pulp industry, but they use it as only as energy source, which means it's a huge underutilization if we consider the huge potential that lignin has to offer. Now, if we look at the chemical structure of lignin, we can see it mainly consists of three main monomeric building units that are basically aromatic rings with different side chains, either hydroxyl, carboxyl, or methoxy, which means that it has a polyphenolic structure. It doesn't only provide mechanical stability, because this is the role of the lignin in the plant. It provides the rigidity, but it also can offer different functionalities, that being, for example, antimicrobial, antioxidant, or UV resistance. And this is what we try to figure out here, how we can further utilize the lignin as a biosource. So this is the first thing we tried, by using the lignin as additive for 3D printing. How do we do that? First, we compound the lignin with different plastics, like the PLA or PPA, using our double screw extruder, which we have it exactly next to the biorefinery pilot plant in our laboratory. And then upon compounding the lignin with the plastics, we get these filaments, lignin plastic filaments, and then we use them for the 3D printing process. And from that, we are able to get different shapes and structures. We even try to do a bottle opener or maybe reusable spoons and so on. What we really investigated here is to see how we can homogeneously disperse the lignin with the plastic, so we don't compromise the final products, but also offer new functionalities to the material. What we also tried to do in terms of utilizing the lignin as a biosource in our Polygon project, which was a huge project between different industrial partners and research institutes, was to check how further can we utilize lignin as a biosource. And here I tried to summarize 3 different applications. First one being lignin aerosols. Aerosols are a very lightweight material, basically 90% air, which gives them distinctive properties in terms of insulation or as adsorbents or even as drug delivery materials. So we tried to use the lignin as a monomer for the production of lignin bio-based aerosols, different systems. And what we also investigated is lignin polyurethane foams. Most of you are familiar with the polyurethane foams, or you have it in your daily life, in your sofa, your mattress, or even the inner parts of your car. These polyurethane foams are produced from petroleum-based materials that are very bad for our environment and toxic. So what we try to do is to replace part of these materials by lignin and check how what added functionality we have. And through this study, we also saw that the lignin can reduce the flammability of this material. So which means that we can also replace part of the chemicals we use to enhance the flammability of this lignin polyurethane foams. The third application we did was this extruded or expanded plastic foams. And here in this image, you can see expanded lignin polystyrene foam, where we use the lignin in 3 different weighted fractions to see how much we can use lignin, what is the added functionality without compromising the final product. Because these are the questions always that you want to answer for the industry in order to help providing bio-based materials to the industry. So most of you are very well familiar with these 2 types, the polyurethane foams or the plastic foams, but maybe not with the lignin or bio-based aerosols in general. And here I want to emphasize how the water can help produce these bio-based aerosols. So first, we have these biopolymers in different natural sources, like, for example, like the plant we just talked about, the lignin or the cellulose, or the algae, where we can also extract alginate. These biopolymers are super hydrophilic, which means they are highly soluble in water. We can use the water as a solvent to solubilize these biopolymers. Then we can induce the gelation, which then we would have the porous interconnected network. If we are able here to remove the water from this small mesopores, we can then have a very nice porous structure, which is, as I mentioned, lightweight with low density and have distinctive properties. For example, thermal insulation, as you can see here, the flame doesn't even go through the bioaerosol. But the question is how we can remove the water from these small pores, because usually when we have the water in the pores and we want to remove it, we have the capillary forces that exert stress on the pores, leading to their shrinkage and their volumetric collapse. So what we do here in our university is that we try to use supercritical CO2 drying by having this supercritical phase, which we no longer have these liquid liquid gas surface tension or the capillary forces, and then we are able to keep this porous structure and these distinctive properties. So far, we have talked about how water can help us extract very interesting materials from the nature, or how to produce these nice materials. But for us, after producing these materials, water becomes here maybe not our friend anymore, because as I spoke before, these materials are super hydrophilic. In this figure, you see what happens to materials that when they come into contact with a water droplet. In the second row, if the material is super hydrophilic, the water droplet would come into contact with the surface at 0 seconds and then directly sink in upon 180 seconds. Could be even faster. That depends on the surface of the material you have. But if your material is hydrophobic, then the water would just stay on the surface. Now, what happens if the material, if the water droplet sinks into the material? It will go into the pores, and as I explained before, we will lose the porous structure, and then we lose the structure and the properties we tried to attain. So what our only solution is to hydrophobize the materials to prevent them from this water problem or damage. And that's what we did with the plasma coating, for example. This is a biopolymer aerogel, and up on the plasma coating, now it's super hydrophilic and water is no longer a problem. Here's a short video on how we go from biomass to bio-based aerogels, which I'll walk you through. As Professor mentioned, we start with annual plants like wheat straw. We add them into our cascade in the biorefinery, where we work with hot water to dilute the biomass, remove the as you can see now, we start with the hot water, we increase the temperature and the pressure to start removing the hemicellulose and cellulose, and at the end we have this brownish material, which is lignin. By the way, this is me. I take the lignin, I go to the lab. With the help of a cross-linker, I'm able to gelate it into this bio-based gel. And then with our technology, I take it into our autoclave, where I use this supercritical CO2 drying I spoke about earlier, which you can see now, pressurizing with the CO2. And at the end, we have this very nice material that did not lose any volume. And after that, we investigate the properties. And here I'm just testing the thermal conductivity of the material using hot disk analysis. And yeah, that's the end of the video. I hope you enjoyed. And what we also have is and we also we are trying with the topic of bridging research to industry, as I spoke about before. We have a startup of THH that works on utilizing lignin for consumer products directly. Shall I continue? Or the professor will take over?
Okay. Thank you very much, Razan. We fly back to myself. And I hope you have seen that always making the research, we go from the really micro scale when we look at the pores and the interaction of water with the pores, how to dry it, how to put it in, how to remove it, how to use water as a solvent. And then at the end, we always, as engineers, we have a solution. So we have an application in mind. And by having this application in mind, we are trying to bridge the gap between the fundamental research and the industrial application. And three of my former PhD students, after completing their PhD on the topic of the biorefinery, exactly what Razan was showing now in this small video, decided to make a company out of that, because they were so convinced about the lignin out of biomass, which was treated just by water, not by organic solvents, but by water at different pressure and temperature, that they told this lignin should be very useful for the different life science application where you don't want to have any organic residues, any solvent residue inside. So they have formed as a small startup, LignoPure, which is working now since 5 years approximately, and have now over 30 people working with them. So they are growing and they have their own production. And this is the way how they got where they are. So they were believing that the renewable sources in the combination with water as a working fluid can bring the non-eatable biomass or some industrial residues to the sustainable products. And these sustainable products are all based on lignin, and they're working on the lignin as a solution to replace plastic. Razan has shown you how we replace a part of plastic into the polyurethane forms and into the actually different polymeric foam-like materials. But what we can do by this is also to replace also the microplastic. So they looked at the application where we have this microplastic inside. And as all of you know, maybe there is the cosmetic application like sun blockers, like sun creams, and so on. So they have replaced the microplastic by this water-driven materials, so by this lignin. And what you see, there are these two products which they created, ligno-based and ligno-pearls. There's small lignin particles are entered into the different cosmetic product instead of the microplastics, overtake their function, overtake also the antioxidant function of the microplastic what was inside before, and then we can replace the PE and PP, so polyethylene, polypropylene. So this is two largely utilized products, utilized plastics there, and then it can also replace the titanium dioxide and also oxybenzone, which are added as a UV antioxidizer like the sun blockers as well. For sure, these are very high value application. We can also go to the low value application, not to utilize the lignin as a partly supplement in the production of forms and different plastics, as we have explained before. So this company is using the different weight, and we are actually very, very proud of them because they went all the way from our basic applications to the allowance and to the legal framework for the in such a way produced lignin in the cosmetic product and in the different life science application. And maybe you know this is a huge, a long way. It takes a lot of effort, but they are now so far. So we have at least one product which we can make under this in this sustainable development and this sustainable process, starting with the biomass, utilize water as a working fluid in this case, and coming all the way to the additives in the cosmetic formulation. So this is a plant-based multifunctional ingredient here, which you see on their production sheet. So we hope that this is not the end, but this is just as a start from the many, many different products which we can make out of this water-based process, out of lignin, out of different biomass. And we have done also with the same lignin already very successful trial with the Tesa company, which produce actually these tapes. And these tapes, maybe you know it's through the 3M or Scotch as a Scotch family, but in Europe Tesa is very popular. So we have the tapes with the additive of lignin instead of plastic, instead of different anorganic materials. And there are also successful trying, which you have here. And we have one more very important feature. If we use natural materials like lignin and we use only water in the production, then the product is biodegradable. So we can look at the life cycle of our products from the very beginning as a biomass up to the end into the earth and maybe new biomass growing on that. So this is something what we would like to follow on and hope to make a reasonable contribution here. And all these thoughts are also valid not all for my laboratory and for my institute, but also for the common our common university hub with the INWEH Institute with Professor Madani, where we have from our side 2 different research clusters, and one of them from Professor Shokri. He was also making contribution in this lecture series before. He is concentrated on global soil health, water and climate. And our second research cluster, which is headed by myself and by my team, is the circular technologies for the bio-based materials. And I hope I could show you this way for the bio-based materials coming from the biomass to the product. And now we are working on the circularity of these materials. And if you want to learn more about this, please visit the homepage of our UNU hub. And we are very proud that we have got this so we have got this opportunity in cooperation with INWEH Institute in Canada, and we will follow up on this direction of circular technologies for bio-based materials. And within that, we finish our talk, and Razan and myself would like to thank you for your kind attention and hope that we could continue continue our research, and we could convince you that water is not just a very big abundant product for the daily life, but this is also something which is a working fluid for the chemical engineering, and we can replace organic solvents by water if we know exactly the conditions. And thank you very much for your attention. I hope you enjoyed it at least a little bit. Thanks a lot.
Yeah. I think I should just say that I am blown away because I'm in love with technology and the fact that water can play this significant role in a new dimension as you presented is quite fantastic as far as I'm concerned. But before I start to pick you on some of the things that drew my attention, someone actually asked this question, and the moment the question popped up, the next slide pretty much answers the question, for me, but I'll say it anyways. It says, interesting applications on water as working fluid. I was wondering how such information and applications could help with contributing to the UN SDGs. So I would like you as the speaker to speak to the question, even though I know you've touched on that.
Yes. Yeah, thank you very much actually for the questions. So what you maybe you look at this slide, for instance, because I have the particular SDGs here. So if we speak, for instance, of the climate action, and if we speak about the 13 and 14, so when we look at the chemical plants which are working right now, we have several problems. We have the problems that we utilize the water, but we have emissions, and we have also organic solvents which are coming inside. By replacing the organic solvents through water, we can also eliminate a problem that we have the emissions of the solvent residues in our water, which we also give back to the environment. So in every big fabric, every big plant, we have the wastewater, and this wastewater quite often have some parts of the organic solvent. So it's still regulated, how much organic solvent should it be, but it is inside. When we use just water, we don't have, let's say, wastewater anymore, right? Because our water is the working fluid, and we don't have this organic problems in this regard. Another thing is that right now we use, for instance, the lignin. Razan told us in such a nice way for energetic purposes. It means we just burn it. right? So we just burn it, and this is the lowest level for the usage of the resources. So it means that if we take the energy from the more sustainable sources, and we don't burn the biomass to produce energy, but we use the biomass to produce more complex organic compounds which are already inside, just to isolate this. Again, we can contribute also for the climate action, and this in this regard very easily. So that is just two examples, no? And there's for sure many more. Also the same for the soils. If we have the biodegradable products, so we don't have this waste problem, the waste depots which we have near the industrial sites. Again, this is reduced. So we hope that this valorization of the biomass by water is really a very pronounced action towards the bio-based economy in this sense.
Yeah, I agree with you. In fact, the moment you touched on replacing microplastics,
Yeah.
so the options are limitless as far as I'm concerned. Yes. So I really look forward to seeing more of this. And because I also like aesthetics, already I'm thinking, oh, so many things are going to come out of your lab, from good, aesthetic furniture, regal and all that. So I'm excited in that regard. But there's always a but. And I want to believe that the person that actually threw in, the applications and how they're contributing to UN SDGs are also looking at this from a different perspective, So the first one for me will be in terms of the volume of water. Because we know you talked about Hamburg being very rich in water. You have a lot of water, so it makes sense to want to play around, water in that regard. But in geographic locations where there is scarcity, and we're hearing of how more we can use water for industrial use in this regard, even though they're sustainable. What would be your take on that? Is it something that can be explored, and all that? So talk me through the volume of water vis-a-vis, these innovations.
Yes. Yeah, so this is for sure a very important question about the availability of the resources, right? So this is a question which we have in the chemical engineering always, doesn't matter which resource is that. It can be also crude oil, it can be biomass, it can be actually anorganic chalk, which are using, for instance, for the glue masses, for the production of these tesa films, which I have shown you before. So this is a completely, this is a very important question. So one thing which is, I can tell you that for the biomass, in order to make this dissolution. So in order to make this whole process to produce these lignin, which are using, for instance, here, or maybe I go a little bit less. So to produce this lignin out of biomass, we need 9 parts of water and 1 part of biomass. So 9 times as much water as biomass, what we do have here. And so this is something what we can already see now. It sounds a lot, right? So let's say for 1 kilogram of the biomass, you need 9 kilograms of water. But don't forget that we don't waste this water. We recycle this water again. So we can have a whole closed loop of the water which dissolves our products. So we take out, for instance, the lignin, we take out the cellulose, but then we can completely close the loop and take the water back to our process, because it was not mixed with any further organic solvents or anything like this. So this is actually an answer. It doesn't mean we need the fresh water every time which we run this process. The second important issue is we can use this process which we have shown you, as you see here. We can use this as a batch process. So it means we have here a relatively small plant which can be used for the biomass available on site. So we have done it with the straw, but it can be also done with all other types of the biomass. So you don't need a huge central factory somewhere. You can make a decentralized production on your spot, and then you have some starting amount of water, let's say, but you can mainly recycle and reuse this water. So already a plant having, let's say, 100, 200 liter capacity is already useful. And since we have only water as a working fluid, this is not, you don't need a special exhaust, you don't need any wastewater treatment or something like this. It means also the person with not so highly specialized qualification can drive this apparatus. So you don't have the hazardous materials. So this maybe it's our motivation as well to do it like this.
Interesting. So if I want to retire into this, all I need to do is just come to you, talk me through it, then with about 100 and 200 liters of water, we are good to go,
Yes.
So be expecting me. Anyway, another question, came along. It said, couldn't agree more. I'm blown away. Thank you. But can you talk a bit about plans to scale some of this up, especially some of these uses, especially the SPF and the microbeads, and the benefits of these two in terms of also distribution and how to ensure equity in this regard? I hope the question is clear.
Yeah, so this is a question addressed first of the different biomasses, not different plants which can be used for this process. It's one of the important questions which we could answer already, at least partly. So all annual plants, actually doesn't matter which of them, can be a source for this process. And if you make this on site, please remember the plants, doesn't matter which plants, have a huge amount of water in them. Normally, whenever we use this plant for the production, we first dry them. We don't need this step here. It means also the fresh biomass can be utilized here in this process, and we can account for the water which is inside the plants. This is true for all types of the annual plants, and these are quite mild conditions which we need for the annual plants. Then for this technology, we can also use the wood rests, so it should not be the whole wood. It doesn't matter which part of the wood we actually use. So when you have some wood, let's say based factory, I don't know, you have a furniture production or something else. Normally you have some rests, right, which you cannot use for your main product. And these small rests still can be utilized. You can chop them and then you can utilize this here inside. And then what we are producing a powder, so we are producing particles which are easily to be transported. So in this case, we can use a very standard transportation system to drive them, let's say, from place A to place B. And in these regards, we can also have a very good logistic solutions. But what I can tell you, if we think about the raw materials being transported to the plant, the calculations tell us that it is feasible if it's, let's say, around 100 kilometers around this plant. So if we make the decentralized plant and have an aim to transport the biomass from the surrounding to this plant, it should be somehow around 100 kilometers in this range. So so this is the boundary conditions which we must have. We cannot improve this. So if we, let's say, have a country where we have to drive the biomass through the whole country to this plant, it's not feasible anymore. So to the factory should be near the biomass sources.
Okay. My colleague has a question. Martin.
Yeah, hi, Professor Irina. It was a very fantastic and presentation, and it's a totally new thing that we haven't seen before.
Yeah.
So yeah, we are very excited to have you on this presentation. Few questions. You need energy for this plant. So did you have any assessment of what could be the energy source? Because you had to have heat, water, you have to have pressure and heat.
Yes.
Using that, and what are the energy source for that? One. Second, what stage now you are in the technology in terms of massive production of the technology, exporting it beyond Germany?
Mm-hmm. Yeah, thank you. Thank you for the question. The energy is for sure a very important issue, and that is why we made the calculation. So in this to heat up the water, so normally you use the electrical energy. This is the most powerful one. So basically what we can do if we have any solar plant, solar battery around, so we convert it in energy and then we can heat up this. For the pumps, we need the electrical energy. This is for sure. So we cannot work with any other type of the energy for these systems. But this is what we have to go to. We have calculated the energy demand for this process, and at the end, this is the price of the final product. So if we accept the standard prices for the electricity in Europe, we still can produce the products which can be sold out, and that is why we have shown you this little example of one of our startups, because they have to sell the products, right? Otherwise, it's not feasible. So the energy demand is here reasonable. Also, for sure, as all of you maybe know, to heat up water asks for more energy as to heat up any organic solvent, right? But then we don't have the environmental issues. So the technology readiness level is very high. So basically, we do have biorefineries in the world already. So when you look at the ethanol and the bioethanol production, there are the biorefineries, and our technology can be added to the existing biorefineries already. So it is there, and we are now in discussions also with different agencies to make a demonstration plant out of that. And as I told you already, our startups, the LignoPure, they are already working and producing that. So they are having also a patent on their technology, and they are ready to license it to any other companies which are interested, let's say, in this regard. So you can also realize the whole cycle, so the whole chain on site, but you can also realize just the parts of them. Let's say if you already have some pulp production on site, pulp and paper, we can add this technology of the lignin utilization to this existing pulp and paper factory. So we are flexible on that. And this is a huge advantage, the flexibility of this. So yeah, we can export the technology if people are interested.
Thank you.
Yeah, thank you so much. We've run out of time, and if you allow me, we will go on and on because this is really so interesting. So from my end, I want to say thank you again, Professor Irina and Razan. I wish you all the best in your work. Thank you so much. And for everyone who had been a part of this presentation, I'm sure your curiosity, has been met in a way, and I believe you're also looking forward to seeing more products, from this innovative approach, especially one that has water at the center of it. And I'm sure you also appreciate how this ties well with contributing to UN SDG goals. So from here, thank you very much to our speakers. Thank you once again. We look forward to welcoming you to another interesting talk next week. Everyone, thank you. Bye for now. Take care.
Bye. Bye-bye. Thanks a lot.